Sunumları
And then we have take a break and
Ben direkt
start to another speaker just about the 5 minutes.
Tamam.
Tamam başlat. Sen başlat. Tamam.
Andrei, good morning. Can you hear us?
Good morning, Feza. Yes, I can.
Okay. So probably Gilson had a time problem. So would you mind if we start with your presentation?
That's absolutely no problem, no.
Okay. So you're very welcome to the meeting, and we are very proud that you are joining us. Can you hear us? Can I kindly ask you to share the presentation? I think there's a share button. Time problem. So would you mind if we start with your presentation?
That's absolutely can hear myself again. I don't know why.
You're very welcome to the meeting, and we are very proud that you are joining us. Can I kindly ask you to share the presentation? I think there's a share button. Problem. So would you mind if we start with your presentation?
That's absolutely can hear myself again.
Sanırım teknik bir sorun var arkadaşlar. Ondan sonra şey yapabilirseniz, ses çünkü yankılanıyor. Ben kapatıyorum kendi sesimi ama Andrei sanıyorum bir daha bağlanacak. Fatma Nur, günaydın, hoş geldin.
Günaydın hocam, merhaba.
Fatma Nur da şu anda Japonya'da hocam. O da bir toplantıda sunum yapıyor. Fatma Nur, Andrei'yi bağlanmakta zorlandı. Tekrar geldi. Tamam, harika.
Yes, I think I figured it out now. I'm sorry.
Okay. I'm turning off my microphone so it will not
Yeah, absolutely. Sorry for that. It's my Zoom being weird.
That's
But
okay,
yeah,
no problem. Not technology.
I'll just go ahead and share my screen then if that's okay, and we start.
Thank you very much for joining us.
Yeah, thank you very much for inviting me. Cool. Give me 1 second to share. And you can see my slides in a proper format. Excellent. So this small talk on what we've been doing on aluminum manufacturing here at the University of Southern Denmark is mostly driven by my wonderful postdoc Fatma, whom you are very well acquainted to. She's a blessing, you know. She's at a conference in Japan right now, so I think she's slightly jet lagged, and I don't know if she can join. She is in the list already, so that's great. The effort is mostly concentrated on the surface roughness properties of printing aluminum silicon tin manganese feedstock on a unusual setup. So it's designed for a 700 watt machine. We are going on a 400 watt machine, and that brings some challenges around. But before we reach the surface roughness, we even had to tackle the fact that these machines are not made for this powder, and that comes with some challenges. So just to briefly introduce Fatma, she should be the one basically talking, but she's a postdoc here at the Center for Industrial Mechanics at the University of Southern Denmark, and I'm an assistant professor that is supervising her work. And together we've been doing a lot of fun things, I think, and one of them is exploring this novel non-explosible aluminum powder from equispheres. So why is this even interesting? It's because as opposed to normal aluminum silicon tin manganese feedstock, this has a non-explosibility claim. If you look at the ASTM standards, it's actually less explosive than normal 316L powder. And of course, that sounds a bit too suspicious to be true, right? So we actually did a preliminary study, which I'm going to speak very briefly about, on the explosibility of this to begin with. So the first thing we're going to discuss is some characterization on the powder, the explosibility tests we did with some partners in Japan, unrelated to Fatma's conference, it just happens to be there. And then we did some optimization, of course, to manage to handle these challenges that come from the powder not being designed for a 400 watt system, but from 700 and above. And then we'll, of course, present the results very briefly and run a conclusion. So the whole point of this is that we found 2 years ago, I believe, we really wanted to move towards aluminum. We were, happy with printing steel and Inconel, even copper, but aluminum, as we know, is a reactive powder. And this comes with the need for accreditation for the environment, and it infers environment costs above that of the machine. So what we were looking for was an option of printing aluminum without having to invest potentially more in the environment than we did in the machine itself. And that's when we stumbled across these guys from Equispheres. They're from Canada, and we've had a very, loving relationship ever since. So they formulate an aluminum silicon tin manganese feedstock, which they claim is non-explosive. They also make standard explosible, let's say, powder, along with a lot of other cool things. But this one in particular served our application. So the first question is, how is this non-explosible if it's just the same formulation? And while their recipe is still a secret internally, we think we have a very good idea why. So first of all, the homogeneity between the spherical particles is very, very high. As you can see in the picture, they are very spherical. They are very large. So most powders are within this 15 to 45 or 53 micron. The D90 of this powder is above 100 micron, or slightly above 101, 102 micron. We suspected originally that there's some coating done to the particles as well to prevent this chain reaction happening in the oxidization, but this is not the case. So basically what happens is that if you do have a very fast oxidization, which is this burning, right? It's inhibited past the first couple of layer particles. So basically the contact area is so nice because the spheres are so large and so fine that you don't really create this nice energy flow through the powder. But of course, that's very good on paper. We had to test it properly. So to characterize this, we performed together with our partners in Japan. We performed 3 explosibility tests. First of all, looking at the lower explosibility limit. So where does it start exploding? What is then the minimum amount of energy required to explode this powder? And then if the explosion should happen, what is the maximum explosion pressure you can expect? And these are, of course, standardized. They are standardized to Japanese standards, but there are equivalents in ASTM as well. And in 2 of the 3, it turns out that the Japanese standards are even more rigorous than the ASTM ones. After we characterized it, we did our process parameter optimization on this. So we ended up doing basically shooting blind in the dark because the powder had not been designed for this wattage. So we used the volumetric energy density as a guideline, but as we very well know, it's not the only marker that speaks towards the success of a powder or not. So we went for the maximum power, or slightly close to maximum power, 390 watts in our system. We didn't vary the layer thickness, but we did vary the laser scanning speed massively together with the hatch distance. And this gave us volumetric energy densities between roughly 30 and 65 joule per cubic millimeter. Then we did an analysis, density characterization and tensile testing, and we also have surface roughness, which was the whole point of this study. But it's kind of weird to talk about surface roughness if you don't really trust what you have printed to begin with. So the whole thing plays into the same scheme. The way we did this is by doing a 12-stage study where we varied a lot of different parameters, ranging from the border parameters, hatching offsets, the printing sequence, and the upskin, downskin together with the border and hatch offset. And there's combinations thereof. And this work is inspired by Ramiro Cedillo, who did it on not aluminum powders, but still a relevant feedstock. The results themselves, talking about the explosibility first, the NEXP1 powder, this is the non-explosible powder from Equispheres, is compared to 2 Japanese large manufacturers. We're not allowed to disclose the names, but these are the standard powders you would buy on the market. So as you can see, the range of this test goes up to 300 millijoule. It doesn't even count afterwards. And we added 300 millijoule to this, and we could not get it to explode. So basically, we were outside the boundary of what the test even looks for. When you look at powder A and powder B, they take at least an order of magnitude, if not more, to explode. So this basically indicates that this has significantly superior safety in terms of what it takes to explode it. The second thing was, if you are to ignite it, you would need at least double, if not triple, the energy compared to powder A. So once the dust is exploded, you will find that you are still very much in a low risk area. So you're very close to being at the limit again. This time we could actually fit in the range, but it's significantly, I mean, it's overwhelmingly low, the risk of exploding this and the energy it takes. And if you do explode it, there are 4 categories according to the Japanese standards. So they go from 0 to 3, and powder A and powder B are finding themselves in 2 and 3, and this one is in powder A because it could not actually get to explode. It took so much energy to get it to explode, and the pressure, even when it exploded, was so low that you could contain it in a tiny glass. I've seen it with my own eyes. So basically, it rates as a non-explosible feedstock from any perspective. So this gave us a good confidence to try it on our machine, which was not, I mean, the machine is ready for reactive powders, but the environment around it is not ATEX. Although when I first did it with my engineer, we were, all hazmat suits up, and we were holding each other's elbows when we were pouring the powder, so we didn't risk any kind of dust cloud forming. So once we established the safety of this powder, we were ready to do a characterization. And again, we did a study ranging, if you recall, the scanning speed and the hatch distance, and we got vastly different results. We were in constant dialogue with the company because they, again, they formulated this powder for 700 watts and above. So we talked about what could important markers be here. And it turned out that the hatch distance was indeed super important in limiting the porosity of this. And if you look at the samples with 011 and 012, the ones that are highlighted in red towards the middle of the screen, they do display very good porosities. So we are at above 99.5% densities on this powder, which is not made for this wattage, which is super interesting. The tensile results are comparable to those of literature. So we are not uncomfortable recommending this powder as a good alternative to standard aluminum silicon manganese feedstock. Of course, it's dependent on parameters, and if you can notice in the graph, we have a higher strength that you get for the 1100 millimeter per second scanning speed versus the 1250. It also makes sense. The trick is to find the sweet spot, because if you go too low, you also risk damaging the melt pool and creating keyholing and so on. So this is in line with what we found in literature for standard aluminum, which I think speaks for itself of how relevant this is. On the surface roughness, this is actually the major caveat, the major drawback of using this larger spherical powder. And as such, that regardless of what you try to do, you will still not really match the quality or the planar aspect of a normal feedstock in aluminum silicon tin manganese. Simply because you will have slightly unmelted powder particles, but also because if you saw the density analysis before, this was done on the bulk part. It's really, really different in its behavior from the bulk part, the center of it, to the boundaries. And that's where we struggled a lot to get something meaningful to begin with. And at some point, the company was also, running out of ideas, and, Fatma was also on the verge of going crazy. And in the end, we came up with an idea of varying these parameters in terms of upskin, downskin, and infill. So if you look at the graph, you can see that we still get very good roughnesses, especially for 9, 10, 5, and so on. So these parameter sets are the ones that relate to varying the scanning strategy. So it's not so much about the hatching distance. It's not so much about the power and the speed. It's really about in which order do we handle this. And Jose Muniz from Ecospheres was very helpful in this regard. He's one of the guys who formulated the powder. So if you look at the best and worst results from the study, parameter 9, where we took the downskin infill and upskin order, is close to 2 micrometers RA, whereas parameter 11 is close to 10, in which case we don't control the upskin and downskin. So basically the finding of this is that for surface roughness, what's really important is the sequence when we talk about the boundary, the sequence of downskin, infill, and upskin. For density, it's much more dependent on the hatching distance and the speed. But still, regardless of this, we can match or come very close to, if not exceed, the aluminum silicon 10 manganese, which is the normal explosible feedstock, while having the benefit of it not being explosible. So basically, to conclude, the explosibility mean that this powder is overwhelmingly safe, basically. You are safer according to the same standards than actually steel. It's not part of this study, but I've read the standards. I've translated the Japanese standards to the American standards for 316L, and they are actually, we are less in danger than we are for 316L. So when we talk about the drawbacks of this, we need to address the boundaries, and we're still looking into ways of optimizing it, and the boundaries are dependent again on varying the order of scanning. So we have the downskin, infill, and upskin. When we talk about porosities, we are confident that we can match those of the normal feedstock. And the major selling point of this is that we did not have to invest anything extra into our facility before we managed to print reactive powders, other than having a machine that's ready for reactive powders. So none of this extra ATEX accreditation and whatnot. And that's a very, very impressive thing, I think. So I can only recommend that Equispheres is contacted. Yeah. So basically that's the short talk I wanted to give. And again, very much thanks to Fatma for performing the vast majority of this work. If there are any questions of any sort, I'd be happy to address them.
Professor Andre, thank you very much for great presentation. Just I would like to ask, some, question. If not related, I'm so sorry. Forgive me. So I think that, material is microscales, right? So do you think if you use it, nanoscales, this nanoscale will affect your result as a positive or not? Do you think anything else? An idea?
I'm sorry, could you repeat that? If I use the powder in what?
Your powder is microscale, right?
Correct.
I just offered that if you use it this nano powder is scale is nano.
Right.
Nanoscale will affect your result more or any positive or negative result.
I understand now. I think it's a very valuable question. So if you think about the benefits of or the reasons for which this is not explosible, it comes from the fact that the spheres are quite large. So they are actually double the D90 of a normal powder feedstock. So if we go to a nano scale rather than on a micro scale, this would go somehow against that which we saw as a benefit here. I have some extra slides actually about the microstructure analysis because Fatma has a lot of time on her hands, so she just does a lot of extra things. But what we see here is a matching scanning strategy to account for the fact that this powder is very large. If you think of the reason for which it doesn't explode is because the contact area is very small, and of course you have a very valid point.
Yes, you're right. Yes, you're right.
If it's on a nanoscale, of course, in principle, the contact area is even smaller, but then you really, really must control the sphericity very well.
Yeah, you're right.
So I think that's really the major thing here, how spherical it is, not necessarily how big it is.
All right. Thank you very much for great, presentation. And then actually I got a so great contribution for us. So thank you for everything.
Yeah, thank you for having me here.
Yes.
Yeah,
Of
Andre,
course.
thank you for your talk. Very nice talk. We learned a lot. Do you think we can use this material in the medical field? Like we are willing to use magnesium implants because they are resorbable, and magnesium is the one of the trace elements in the human body. So do you think these are appropriate because they don't explode? And you can kind of work on them?
Sure. I think that's a very relevant question. And of course, magnesium is fantastic for its compatibility with the human body, but it also comes with the very big risk of being the opposite of non-explosible, right? So I think, of course, there should be a biomedical study done on this powder specifically. Yet it doesn't have any components different than normal aluminum, silicon, tin, manganese. So if you look at its chemical composition. So within certain boundaries, I think it's very worth exploring the benefit of it not exploding versus how biocompatible it is, because there's also a degradation time, right? So if you only have to take some implants that don't need to be there for 6 months, or if you only have something very temporary, I think this could be a very good way to move forward.
Yeah, maybe we can work together on that. And
I think we should definitely work together on that.
And thank you very much for your contribution. It was very valuable to us. Thanks for the time.
Yeah, and thank you for having me again, and thank you for Fatma for doing all of this study.
And we hope to see you soon again in person, hopefully.
Yeah, we're planning a visit very soon, early next year, as you might know.
Okay, thank you.
Thank you.
Hocam, the floor is yours. Thank you, Andre, and we can proceed with the next talk, maybe. Thank you very much.
Thank you, Professor Andre. Next speaker is Dr. Ayşenur Gencer, and his title is Investigation of 2D Materials for Hydrogen Production Performance. So, Professor, please come here.
Okay, good morning, everyone. I'm Ayşenur Gencer. I am an associate professor at the Karamanoğlu Mehmet Bey University. And today my presentation title is the investigation of 2D materials for hydrogen production performance. Here is my outline. I will start with an introduction, including 2D materials, photocatalytic water splitting, and density functional theory. And then I will move on to our calculations for these materials. And we perform calculations for the structural optimization, stability considerations, electronic properties, and water splitting performance. Then I will conclude my presentation. After the discovery of the graphene, the interest for the 2D materials is increased, and a 2D material is a material with a single layer of atoms, and they have reduced dimensionality, and this provides them unique properties. Here you can see graphene, transition metal, dechalcogenides, and hexagonal boron nitride. These are examples for the 2D materials. These materials have high surface area, exceptional electrical conductivity, and mechanical strength. With these properties, they have lots of applications, such as in the electronics fields, energy storage, photocatalysis. And today I present our studies on the photocatalytic water splitting. And what is photocatalytic water splitting? It is one of the hydrogen production methods, and we have 3 main processes. First, a photon is absorbed, and electron and hole pairs are generated. Then we separate these electron and holes are separated, and then the surface chemical reactions are performed. There are requirements for a good photocatalyst. First, a good photocatalyst has a band gap larger than 1.23 electron volt, and the bottom of the conduction band should be more negative than the redox potential for the hydrogen reaction, and the top level of the valence band should be more positive than the redox potential of the oxygen reaction. And to the materials also employed for the photocatalytic water splitting, and they have high light absorption. This is important for the photocatalytic water splitting. Also, they have efficient separation of the charges, and also they have stability and durability. In addition to the materials, the heterostructures are also used in this field. What is a heterostructure? We stack 2 layers of the 2D materials, and we create an interface between these components. There are lots of examples for the heterostructures. Here you can see an example for the germanium carbide and silicon carbide. Why we generate heterostructures? Because they have optimized bond alignments and they have enhanced light absorption. There are 3 types of heterostructures. First type is shown here. This is type 1 heterostructure, and for this heterostructure, material A has a band gap smaller than material B, and the electrons and holes are transferred from material B to material A. For the type 2 heterostructure, you see here, in this heterostructure, the transfer of electrons are from material B to material A, and holes are transferred from material A to material B. And the last type is the type 3 heterostructure. They have a similar band structure with the type 2 heterojunctions, but the difference between the valence band and the conduction band of these 2 materials is larger in type 3 heterojunctions. Photogenerated electron from the material A combines with the hole of material B, and the electron from material B and the hole from material A participate in the reduction and oxidation of the water, respectively. For this photocatalytic water splitting studies, we use density functional theory, and I want to introduce you the density functional theory. Here you can see the well-known Schrödinger equation. It is a popular equation in the quantum mechanics. And here we have the Hamiltonian. And we can solve the Schrödinger equation for the hydrogen atom. But after then the other elements in the periodic table, it is very hard to solve. And here you can see the many-body Hamiltonian. And there are lots of terms between the interactions between electron and electrons, nuclei and nuclei, and electron and nuclei. Therefore, solving the Schrödinger equation for the many-body systems is not easy. And at this stage, we use the density functional theory. We use electron density to solve the Schrödinger-like quantum equations and obtain the ground state properties for our materials. How we perform these calculations? First, we make an initial guess for the electron density, then we calculate the effective potential, then we solve the quantum equations, and we get the electron density. If our initial guess and obtained electron density is consistent, so we get our outputs. If not, then we turn back to our first stage, make another initial guess for the electron density, perform these steps until we get consistent initial and calculated electron density. For this calculation, we use simulation programs. There are lots of simulation programs in the literature, such as CASTEP, WASP, CSDA. We use WASP. For the DFT calculations, you can have many implementations. For example, for the kinetic energy, you can take full relativistic, semi-relativistic, non-relativistic, or for the wave functions, you can use atomic orbitals, plane waves, or others. Here, I want to introduce you a new 2D material family. It is gets interest after the synthesis of the molybdenum silicon to nitrogen 4. Here you can see the 2D materials including their layers. Here, for example, we have a graphene which have N equals 1 layer of 2D material, and the last one is the molybdenum silicon to nitrogen 4. It has a 7-layered structure, and now they are called Ma2Z4 materials. We get these materials using a MZ2 molybdenum sulfide 2 type monolayer with a indium selenium type monolayer A2Z2, and this new material family could be employed in the photocatalysis, transistors, spintronics, and in this study we choose these materials. Tungsten silicon to nitrogen 4, tungsten germanium to nitrogen 4, and their Janus counterpart of the tungsten silicon germanium nitrogen 4 to obtain their hydrogen production performance. Here you can see their crystal structures here, and these are our simulation parameters. First, we optimize these 2D materials and obtain their lattice parameters, bond lengths, and cohesive energies. Our results are consistent with the literature. Then we move on to their stability considerations, and we calculate their phonon dispersion curves. Here you can see the phonon dispersion curves for these materials, and there is no negative frequency in these plots. Therefore, we can say that they are dynamically stable materials. Also, we calculate the elastic properties of these materials, elastic constants of these materials, because to determine whether they are mechanically stable or not, we need to obtain these elastic constants, and we check the mechanical stability criteria. Our calculated constant satisfies these stability criteria. Therefore, we say that these materials are satisfied the stability conditions for the dynamically and mechanically. And last consideration for the stability is the thermodynamic stability. For this purpose, we performed the open issue molecular dynamic simulations. Here, the plot shows the total energy change along with the time, and the first figures shows the crystal structures at the beginning of the simulation, and the last one shows the crystal structures at the end of the simulation. And we saw some fluctuations in the energy, but they are acceptable. Also, our crystal structures are same at the beginning and at the end of our simulation. Therefore, they are also thermodynamically stable materials. Then we move on to their electronic properties. We obtained their electronic band structure. Here you can see the electronic band structure at the high symmetry points, and all these materials have indirect band gaps. For example, for the tungsten silicon to nitrogen 4, the band gap is from gamma point to K point, and it has a 2.68 electron volt. We get 1.65 electron volt for the germanium one, and for the Janus counterparts, we have the 2.12 electron volt. As I said, a good catalyst should have a band gap larger than 1.23 electron volt. They all satisfied the band gap criteria. Then we move on to their conduction and valence band levels to determine whether they are suitable for the photocatalytic water splitting. Here you can see the conduction and valence band levels for all these three materials. For the pH 0, only the Janus counterpart satisfied the appropriate conduction and valence band levels. However, if we change the pH value in the environment, the conduction and valence band levels or reaction energies are changed. We use this formula to determine these levels, and we found that the silicon one is a good photocatalyst from pH from 3 to 14. And for the germanium one, it is a suitable photocatalyst at the pH from 1 to 7. And the Janus counterpart is a good catalyst at the pH from 0 to 12 pH values. After determining these properties, we want to make the heterostructure with these 2D materials, and we choose X cell. X is aluminum, gallium, or indium monolayers. First, we optimize these materials. Here you can see the crystal structure of these materials, and these are the lattice parameters. I want to say that the lattice parameters between X7 and our materials are different. For a good heterostructure, we need a consistent or suitable lattice match. Therefore, we need to make supercells with these heterostructures. Here, as an example, I will show the aluminum xenon and tungsten silicon to nitrogen 4. For the aluminum xenon, we make a supercell using square root 7 by 1 supercell, and for the tungsten silicon to nitrogen 4, we make a supercell square root 13 by 1 supercell, and these are the lattice parameters for these supercells, and they are now suitable for the making the heterostructures. After these supercell generations, then now we put the aluminum selan on the tungsten silicon to nitrogen 4 at the different locations on the layer. These are different stackings. Here you can see. And then we optimize these heterostructures, and we need to determine which heterostructure is the more stable. For this purpose, we calculate the binding energy of these stackings. Here you can see these binding energies, and A1 stacking is the more stable stacking than the others. Then now we are working on the stability of the A1 stacking, the electronic properties of the A1 stacking, and also the water splitting performance of the A1 stacking. This is for the aluminum xenon and tungsten silicon to nitrogen 4. When we complete these studies, we move on to the other heterostructures. In this study, we investigate these materials using density functional theory to reveal their hydrogen production performance. We found that they are dynamically, mechanically, and thermodynamically stable. The electronic band gaps are also suitable for these materials for the photocatalytic water splitting. And also we choose X-selan monolayers, so we optimize them, and the heterostructures with the aluminum selan and tungsten silicon to nitrogen 4 monolayers are studied. And now also I want to talk about our project. Our project title is the investigation of the photocatalytic hydrogen production performance of X-selan tungsten silicon to nitrogen 4 and X-selan tungsten silicon germanium nitrogen 4 heterostructures. It is supported by the Gazi University Scientific Research Projects Coordination Unit. I want to thank all our project team, and these are all I want to present today. Thank you for your attention, and I will be happy to answer your questions.
Thank you very much for your speech. And have you any question? Yes.
One question. You calculate the condition entropy or thermal instability, let's say here. How did you calculate it? Did you choose one stable one and then compare the energy, or you just calculate them individually? Is it clear what I'm asking?
Do you mean the binding energy here?
Sure. Yeah, binding energy. Yeah.
For this calculation, we take the optimize these materials, optimize structures, and also the energy for this stacking, and then we get this value, and it is negative, then we say that they are stable. This structure is stable.
Okay, and the other question is that you created 13 square root and 13 square root. Can you try to rotate a little bit and see or have a
No, I just take this monolayer and make this superstar.
So, Professor, how about the metal organic framework if you configure your materials for hydrogen production?
Now we are not working on the metal organic frameworks. We are working on the heterostructures with the 2D materials, but they are considered
the hexagonal metal organic framework and then configure any metal on the surface of the I think people, supposed recently have been working more about the metal organic framework.
Yes.
And also covalent organic framework. Okay, thank you.
Thank you.
Any question? Thank you very much. Okay. Bağlantı var mı şunlardan? Herhalde Yunan herhalde.
Şimdi onun saati 11.40 göründüğü için hocam.
Tamam.
Muhtemelen onun saatin bekliyor olabilir.
Gilson var mı?
Gilson da gelmemiş.
Tamam. Bir ara vereceğiz büyük ihtimal. İki tanesi yok.
Yabancı.
Onları tekrar kontak kurayım da ben Gilson'un bu bizim arkadaş. Belki bilmiyorum neye geldi onların. Bir de şu Yunan herhalde gözünü görmüyor. Bir ona bakayım. Nopes var ya da zamanı bekliyor.
Tamam, zamanı bekliyor.
Bekleyelim ya. Bir ara versin.
Ladies and gentlemen, we will start to our new presentation in 5 minutes. It's just we are looking for any slides of our authors. If you cannot, she will explain all of presentation as I orally. All right, just 5 minutes to start it like a new presentation. So, ladies and gentlemen, right now our Professor Kerem Pidu is correct. Okay, and then her topic is like an energy as a dual use item under European Union law. So I think in this like presentation, she will explain her topics without any slide. And then please come in, Professor. All right. Coming, Professor.
Çok teşekkür ederim hocam. Herkese çok teşekkür ederim. I'm very honored to be here, not just in Ankara, the capital of Turkey, at such important day before the celebration of the Day of Independence, but also at this university, the Gazi University, and this faculty, the technology faculty, where you do the actual work. I'm coming from a from a much different field, from the field of law, where law comes to regulate what the technology has discovered after it's discovered and after it is under the commercialization phase, with one small exception, I believe. So thank you in advance for all your patience for listening to the presentation. I'm going to talk about energy as a dual-use item under the law of the European Union. I believe that you know much better than me what energy is. I'm going to talk from the legal point of view, I mean, what the law understands as energy, and also what the law understands as a dual-use item and whether these two overlap. Because if they overlap, and why is this so important? It is important because if we say yes, this material or this technology qualifies as energy, or yes, this material qualifies as a dual-use item, then we have the application of the relevant legislation, which means prohibition or extra authorizations, as the case may be, and as we will see a bit later. So how I got the idea came to me, especially about this question, when I saw in the news that an electricity production facility was bombed. And this, the news reporter was saying that this electricity facility was bombed. And it was significant because the electricity that was produced, it was going to two directions. It was going to the nearby military facility and to a nearby hospital. So we can see that it's an item that is not used for one purpose, it's used for multiple purposes. So let's see what the EU understands as energy. And it has a lot of legislation to regulate energy, but I thought it would be better to see the definition of energy under the taxation, the legislation related to energy, to the taxation of energy. And it's interesting because it has a definition that is split into natures. The first nature is to categorize all the products under CN codes. So I'm going to go over them very briefly. As energy product qualifies any product falling under CN codes 2701, 2702, 2704 to 2715, and it also has other codes. So it's just a list. And I'm sure that you, the people coming from technology, can understand much better these terms than I can. And it has a second factor, the definition. The second factor of the definition is an abstract definition. And accordingly, other products, meaning beyond the ones that are listed, may qualify as energy products when they are intended for use, offered for sale, or used as a heating fuel or motor fuel, or as an additive or extender in motor fuels. And the same applies to hydrocarbons with the exception of pitch when it is intended or performed use or sale is for heating purposes. So we see that the second definition is more orientated towards the function, towards the intention of how you use a product. What is interesting is that the dual-use item is defined in a similar manner, meaning that we have a list of items with CN codes, and this list is quite extensive. I think it goes over 60 pages, so I'm not going to go into this. And the second approach, the subjective approach, is the following. Dual-use items stands for items including software and technology that can be used for civil and military purposes, and includes items with non-explosive uses, as well as items assisting in the manufacture of nuclear weapons and other nuclear explosive devices. So we see this, maybe we can understand better the meaning of the dual use. It's something that is used for civil and military purposes. That's how this idea came to me when I heard about this news item. The list, it is important here to say that the list of the dual use items has not been drafted by lawyers. It would have been impossible, I think. It has been drafted by groups of the persons who develop, not who develop, I'm sorry, from persons who have commercialized this technology. It's the Australia Group, the Missile Technology Control Regime, the Nuclear Suppliers Group, and the Wassenaar Agreement. So the companies involved in the commercialization of these items have also made the lists that were then adopted by the lawyers. So I'm quite sure that if one of you could go through the lists, could find items and technology that fall within the two lists, so they qualify both as energy and both as dual-use items. With my almost non-existent knowledge of technology, meaning what I have been taught from school many years ago, I could trace only one item, and these are the lubricating materials in the respective. They have been listed in the respective legislation under the number 1C006. So it's lubricating materials and both other materials, taking into consideration the subjective approach that has been adopted in both definitions. So when it comes to these items, to these materials that qualify as both, the consequence is that they are going to be regulated not only under the laws of energy, but also under the laws of the dual-use items. So even if I have been exceedingly successful and traced only one, which I doubt, item, this being the lubricating materials, the lubricating materials have to follow the legislation of the dual use that regulates the dual use items. So this legislation mandates that all these items have to be authorized before they exit the European Union. And in some cases, they have to be authorized when they are intended for export towards a specific country. Especially to items intended for military end use, where the country of destination is subject to an arms embargo. So again, we go, what is an arms embargo? An arms embargo is wherever the European Union has said that no arms have to be sent. And currently, this is the case with regard to Sudan, Lebanon, South Sudan, Myanmar, Burma, Zimbabwe, Yemen, Congo, North Korea, Iran, Libya, the Central African Republic, Venezuela, Syria, Russia, and Belarus. So in these cases, we need an authorization, and it's also authorization also necessary for items that have not been listed in the dual use regulation, but they are intended for use as parts or components of military items listed in a national military list when these have been exported without the national authorization or in violation of the issued national authorization. So there are some specifics on the authorizations. I will not trouble you with those. I will just tell you that these are necessary. Yeah, so we are done with the dual use items regulation. The other part is that when you have an item that qualifies as energy and also as a dual use item, is that the sanctions regimes that have been decided by Brussels also apply to them. And the regimes that provide for restrictions, and sometimes these are authorizations or sometimes they are just prohibition that you cannot export these items. They are the ones with regard to North Korea, Iran, Myanmar, Burma, and Syria. There's a second issue with regard to energy and sanctions. It is we have to note that in some cases, under some laws that impose sanctions towards third countries, Brussels has decided that energy, as Brussels understands energy, is under sanctions. More specifically, export, transfer, and supply of coal, crude oil, aviation fuel is prohibited with regard to North Korea. In relation to Libya, loading, transporting, and discharging petroleum on certain designated vessels is prohibited. In regard to Syria, Syrian persons engaged in exploration, production, and refining of crude oil may not be granted financial loan or credit. And with regard to electricity, no technology and items are allowed that can be used for the construction and installation of new electricity power plants in Syria. Nuclear energy is a beast on its own, and I think it's the only case where Brussels does not regulate just commercialized items, but also the development, the research. If I'm not correct, if I'm mistaken, please do correct me, because it has decided that certain states cannot develop the technology in order to use the nuclear energy in certain ways. This is the case with regard to Iran and North Korea. With regard to Iran, one needs an authorization before providing Iran with these materials, and with regard to North Korea, this is absolutely prohibited. So in conclusion, I hope that you have taken with you that in certain occasions, an authorization is necessary for certain items, as these are understood under the eyes of the law. And in certain cases, certain items, how you use certain items is totally prohibited, and it has to do with the country of destination mainly. Thank you very much for your patience. Thank you.
So thank you, Professor, for your great presentation. So if any question, if not, let me ask some question. So Professor, is not related with your topics. So people, recently have been using nano-based drugs. So do you know what is the like this procedure in the law? Because nanoscale based drugs is going to everywhere in the body, have some advantages and some disadvantages, such as like this nanomaterial is going to passing to the barrier of the brain, so will give some damage. So right now people also like asking to us. So do you know what is the law saying about that? Because nano-based drug is good, but it also can give it some damage. So what do you think about the procedure of like that, like some drugs, nano-based drugs?
Uh,
You can hear.
yeah, thank you very much. This is a very interesting question. Actually, this was the topic of my last presentation about nanotechnology and how this is understood under the law. I'm afraid I do not remember my last presentation, but I can gladly forward it to you. What I do remember was that it had the definition, the law had the definition of what a nanomaterial is. And it had this threshold of 200 something. I remember the number, I don't remember what it was, what it represented. So I talked about this 200 something, and there was a professor sitting in the audience. He told me, of course, if it does not fulfill it, it's toxic. And I was shocked. That's why I always say that you can understand the lists better than we can. It's a very interesting question, and I will be very glad to follow it up with you.
Maybe next, presentation you can prepare some slides about that.
Just
Maybe
email me.
focus on, yeah.
Just email me, and
All
we will
right,
figure
thank
it
you.
out. Thank you
So
very
right
much.
now we will give you just 10-minute break. So Dr. Lopez, are you hear me?
Yes. Hello.
So we will give some 10-minute take a break, and then if you are ready, we can start with you.
Okay.
Okay, just 10 minutes, all right?
Okay.
All right, thank you very much. Ladies and gentlemen, welcome to another section. Dr. Lopez, are you ready?
Hello, yes.
So if you want, you can button to share to your presentation.
Let me.
So how are you, Lopez?
I'm fine, thank you.
So let me introduce your topic.
Everyone can see the shared screen?
Yeah, we see your presentation right now very well. Ladies and gentlemen, like our author is Dr. Lopez, and his title is Prospects of Laser Processing of Titanium Substitute Titanium Oxide for Designing Thermoelectric Materials. So keep going, Professor.
Hello. Thank you for the organizers in the conference for having me. So my name is Diogo Lopes. I'm a PhD student in University of Aveiro. And today I will be talking about a work which is titled Prospects of Laser Processing of Tantalum Substituted Titanium Oxide for Designing Thermoelectric Materials. So, energy consumption is expected to keep increasing in our lifetimes, thus making the necessity for more efficient and renewable sources to be researched and analyzed. So we have a relatively big inefficiency in most of the processes we use for operations, even for energy production. And here I have the example of a vehicle operation with an internal combustion engine, in which you can clearly see that less than half of the energy used eventually is directly used for vehicle operation, which with almost 70% of it being lost in the process. So this reveals a big inefficiency and a big loss of energy that we are using. And this is not only, this doesn't only happen with vehicle operation, it happens all over the industry, even more noticeable in high temperature industries. So one proposal or one way to tackle this or to help tackle this could be with thermoelectric generators, which can be used to convert this lost heat into electricity. So, as I previously mentioned, it's not only vehicle operation. We have thermal plants, nuclear plants, aluminum, glass factories. So a big array of industries in which a big part of the energy is lost. And our proposal is to use thermoelectrics as a way to directly convert this wasted heat into electricity. This is based with this is done with thermoelectric materials, and these thermoelectric materials are based on the thermoelectric effect, in which we can create an electrical potential by applying a temperature difference into a material, which is called the Seebeck effect. We can also revert it by applying an electrical potential and creating a temperature difference by removing heat in this case, which is called the Peltier effect. In our work, we are most interested in the Seebeck coefficients, on which we apply a temperature gradient in our material, and an electric voltage will be created. So we have some parameters to define our materials, the Seebeck coefficient, which is how the material converts or generates an electrical potential from a temperature gradient. We also have the power factor, in which roughly tells us how good the material is at converting a temperature gradient into electricity. And also we have a figure of merit, which is the best way to assess the efficiency of our thermoelectric materials, which takes into account the power factor, the temperature, and also the thermal conductivity of our materials. So in terms of thermoelectric power generation, these are relatively simple and straightforward devices. These are solid-state devices that will directly convert thermal energy into electrical energy. It is, again, as I said, based on the Seebeck effect. And another big advantage of this type of devices is that they have no moving parts. I'm sorry, they are silent, and they allow for maintenance-free operation. We already have some applications of thermoelectric technologies. Here I have some fields in which they could be applied, which includes military, medical, industrial, consumer, laboratory and scientific, and also telecommunications. And also the example, here we have the example of a thermoelectric module, but in this case it is used for cooling. I think it's associated with a photovoltaic panel. And they lose efficiency if the temperature increases. So I think this is one way to improve its efficiency, not by directly converting it into electricity, but using the other effect, the Peltier effect, to maintain a stable temperature in which the efficiency of the photovoltaic panel is highest. We also have a generator, a thermoelectric generator in cars, some flexible, which could be used for wearables. And also the example of the Mars Curiosity rover, which uses a radioisotope thermoelectric generator in the rover. So, a big part of designing and preparing a thermoelectric module passes by the material selection, which materials are good, and a balance between being a good thermoelectric and being sustainable and not toxic, not expensive. So ideally, a good thermoelectric material is a material with a very high electrical conductivity, high Seebeck coefficient, a very low thermal conductivity, which allows us to keep the temperature gradient. It's stable at high temperature, so we can apply as much temperature as we want. Also stable under harsher environments, and again, able to withstand this as big as possible temperature gradient. However, this is not possible. It is ideal. Most of the materials have some properties and they are not very good at the others for thermoelectric application. And the traditional thermoelectrics, which traditionally is the most known high IZT thermoelectrics that are now used. They usually are high cost. They are made of toxic and rare elements. They also are unstable at higher temperatures or at harsher environments, but they do possess relatively high ZT values. So, as I previously mentioned, this work focuses on tantalum substituted titanium oxide, and the sustainability, availability, and price of the materials is taken into account. In this case, titanium is considered with plentiful supply. Also, tantalum is not considered in threat for now, but the tantalum percentage in each of our materials is much lower compared with titanium. So, with this oxide thermoelectrics proposal, we have some inherent disadvantages of oxide materials, like a large electronegativity difference among its elements, a tendency for carrier localization, a strong scattering of carriers, which can lead to low mobility of the charge carriers and low electrical conductivity. However, we also possess some good advantages with these materials, like their high stability at high temperatures and harsh environments, as mentioned, the low cost, non-toxicity and abundance, and also the ability that we have to design and manipulate the properties of our oxide materials. And these oxide materials allow for the application of these thermoelectric technologies at higher temperatures. So in case of titanium oxide, there are several techniques, methods to improve thermoelectric performance in materials. However, in this case, we mainly used the doping/substitution of our material, although we could also try to promote the formation of nano-inclusions, centering in reducing conditions is also something that we tackle, which will then result in lower thermal conductivities, also increases in electrical conductivity and density. And mainly, when the titanium oxide is doped, it will become an N-type semiconductor. And we can manipulate its electrical properties this way. Another way to improve thermoelectrical properties in the case of titanium oxide is through the processing. So these materials are extremely sensitive to redox conditions during processing. And this way we chose an unconventional technique, which is called laser floating zone, in which we make the growth of a fiber or a rod from the green powders through melting. So again, this method involves the creation of a melting zone. It applies a thermal gradient. It also allows us to have a somewhat oxygen deficient environment during the growth. And also we have some background, as it is already studied, with some thermoelectric compositions. This method also allows the processing of highly dense fibers, which will result in improvements in electrical conductivity. This here is the example of one fiber after growth. So this should be around 1.5 to 2 centimeters. So again, this method is good in relation with the liberty that we have. So we can manipulate several conditions of growth. This depends on material characteristics, like the speed in which we have the rotation. So the feed rod will always be rotating in an opposite direction to the seed rod, and the growth direction is down. We can also use different atmospheres. So as I mentioned, even in air, we have a slight oxygen deficient environment during this growth. However, we can force even more reducing environments by using different atmospheres. So this process is relatively straightforward and simple. We begin with an initial mixture, which we will then mix with the binder, extrude it into cylindrical rods with about 2 to 3 millimeters of diameter. And these rods are then applied in the LFZ system, with the top one being the feed rod, which will give material to the melt zone, and the seed rod, which will be the base in which our crystal or our fiber is growing. So this is, I've been giving a little resume of the background for this work. So in here, we are studying the impacts of this processing in air and also in hydrogen, as well as a post-annealing for samples processed in air. And this post-annealing is done in a reducing atmosphere. So the goals are to characterize the samples obtained, evaluate its thermoelectric performance, and try to establish guidelines for how processing this material using LFZ, what can we get from it. So we expect the ability to prepare this material using LFZ We also expect the incorporation of the tantalum cations in the rutile structure. We also expect the reduction from Ti4+ to Ti3+ cations, which will then result in improved electrical conductivities and improvement in thermoelectric performance. So in terms of characterization, we start with the next RD, which confirms rutile as the main phase in all our samples, which is expected since the degree of substitution we use was 5%, 10%, and 20% of tantalum. So rutile is confirmed as the main phase in all our samples. We also notice an increase in tantalum content leads to phase separation in air, which is also expected. And in hydrogen, so in a reducing atmosphere, a lower tantalum content will result in the formation of the Magnelli phases, since the tantalum cation in the rutile structure in a reducing environment can help stabilize the rutile phase. Here we also have the post-annealing at various temperatures in forming gas atmosphere, which is reducing atmosphere. So for the 10% tantalum substitution, we see the formation of Magnelli phases at lower temperatures. And this is not seen in the 20% substitution of tantalum, again proving or indicating that a higher tantalum content helps to stabilize the rutile phase under reducing conditions. So in terms of microscopy, we have here a scanning electron microscopy and energy dispersive microscopy, spectroscopy. And we see that all samples exhibit a high density, and the density calculations revealed they are all above 90% of the theoretical density. We also can see this particular microstructural effect, which in here reveals a partial alignment of the titanium of the tantalum-rich phase, and also in hydrogen we see again a preferential alignment of this secondary tantalum-rich phase. In terms of thermoelectric properties, electrical conductivity and Seebeck coefficient were measured. We can clearly see that the samples grown in reducing atmosphere show higher conductivity. We also see a general increase of temperature with general increase of electrical conductivity with increase in temperature until about 1000 Kelvin, in which we see a decrease probably related with the phonon scattering. In terms of Seebeck coefficient, we see relatively easily that it increases with temperature and that all our Seebeck coefficients are negative, which means the electrons are the main dominant carrier. So now tackling the power factor of these materials. Again, samples processed in forming gas revealed a better power factor when compared with the ones prepared in air or in air and with the post-annealing. We achieved the highest value of 735 microwatts per meter Kelvin. And the effect of the post-treatment in the reducing atmosphere revealed to be less effective than the growth in reducing conditions to improve thermoelectric performance of our materials. It is also pretty good to see that, especially at high temperatures, this work resulted in an improvement in power factor when compared with some materials in the literature. So, in conclusion, the processing of this material in air and hydrogen atmospheres mainly form a rutile phase with the segregation of the tantalum-rich phase under oxidizing conditions and higher tantalum content. The post-annealing of the samples grown in air resulted in the dissolution of these tantalum-rich phases and with lower contents with lower substitution of tantalum, also in the formation of Magnelli phases, except at the highest temperature. This resulted in the improvement of their electrical properties. As I mentioned, reducing conditions during the laser growth promoted the formation of the Magnelli phases, which again has a positive impact in the electrical properties and thermoelectrical properties of our materials. And the highest power factor we obtained was of 735 microwatts per meter Kelvin at 1120 Kelvin degree. Thank you all for having me. I would like to thank FCT, University of Aveiro, CISECO, and I3M for allowing me to develop this work. And also, again, to the conference for having me. Thank you very much.
So, Dr. Lopez, special thanks to your great presentation. So, any question for these topics? Any question? So, Dr. Lopez, let me ask some question. So, I think you use that, like, titanium-based some derivatives for your laser processing. So, why you select to titanium for that, like, researching?
Okay, so as I shown, titanium is considered an available element, and titanium oxide is abundant, cheap, and non-toxic. So it's
Yes, you're right.
pretty straightforward. Also, which is very important. Also, we have some data in literature about titanium as a thermoelectric, so we have a base in which we can improve.
Yes, you're right. So, Dr. Lopez, thank you for great presentation. And also, laser system is very important, like, especially, recently, in army and medical and another kind of, like, application. So we know that people, trying to get local, laser processing system. So that's why, again, I special thanks to for improving that area. All right, thanks.
Thank you. Thank you very much.
Yeah, you're welcome. All right, right now we, are the like the last authors for this presentation. So that's why we completed all of the presentation today. And then thank you very much for attending all of the people here. Okay, so right now we will finish that presentation today. All right, see you.